In this video we'll go through the 3 rules that we use in Year 12 to differentiate functions. So it's the product rule, the quotient rule and the chain rule. We'll kick this off with the chain rule. So if we were met with this function here and we had to find its derivative, what we'd do in Year 11 is expand it. So 25 take away, what's that, negative 60x plus 36x squared. And then we'd use our rule, so d dx in operator notation, to derive that. So that would be negative 60 plus 72x, which is okay. But what if it was power 5? Or what even if it was power 3? This method of expanding it would be tedious, difficult, fraught with danger in terms of making mistakes, and just generally boring. So I wouldn't do it with a power 3, I certainly wouldn't do it with a power 5, and I certainly would not do it with a power 50. So what we can do is, if we recognise something written like this, we can use what we call the chain rule. So the chain rule gives a method for differentiating such functions, or functions that look like this, used when you spot a function within a function. And we refer to these sometimes as the inner and outer functions. So the chain rule is this thing here, so I'm going to rewrite it here, dy dx in Leibniz's notation as dy du multiplied by du dx. And if you notice something quickly, is those two cancel out, leaving us with dy dx equals dy dx. That is, the derivative is the derivative. So I'll talk a little bit more about what this du means in a sec. Sometimes you might see it written in function notation. I think in the Adelaide SACE they use function notation to write it, whereas in the VCE we use Leibniz's notation to write it. My preference is Leibniz, but probably that's because I've just used or grown up within this system here and it's my preference. But here it is here. So if you have a function f of x and it's composed, or it's made by doing g of h of x, then the derivative f dash x is g dash h of x times h dash x. Alright, so here it is again in Leibniz's notation, and I think the best thing that we can do in this at this stage is try it out. So here's f of x equals this. The inner function is the linear. The outer function is x to the 5, because it's the linear all being raised to the 5. So what we need to do is use derivatives of the inner and outer functions, so let's write them out. So the derivative of the inner function is negative 6, so that derived is negative 6. The derivative of the outer function is 5x to the 4. Now we can also do this using Leibniz's notation by doing what we call a u substitution. So u is the inner function, which is 5 take away 6x, and the outer function then, y or f of x equals u, which is this thing here, being raised to the power of 5. So y equals u to the 5. Now we can get a derivative of both of them, so du dx is negative 6, and dy du is equal to 5u to the 4. Right, so let's use both of these to get our derivatives. Now I'm going to do it with Leibniz's notation first. 1, because it's my preference, and 2, because it's the way it's written on our formula sheet. So dy dx is equal to dy du. Now that's dy du there. So it's 5u to the 4 multiplied by du dx. Now, we've done a u substitution, that is, we've let u equal the linear, 5 take away 6x. So, to write our derivative, we'll substitute u back in. So, 5 take away 6x to the 4, and then multiply that by negative 6. So let's clean that up by multiplying this coefficient here by negative 6, so it's negative 30, 5 take away 6x to the 4, and there's our derivative. Right, we can use it with function notations, so f dash x is g dash, so it's the derivative, And what we've got to do is bang h of x, which is this thing here, into g dash x. So we're going to rewrite that as 5, and instead of writing x, we're going to substitute h of x, which is this thing, for x, multiplied by h dash x, which we wrote out here. Forgot the power 4. That's what always happens when I do this in function notation. And what you hopefully notice there is it's the same derivative. Alright, so let's use it on this one here. So use the chain rule to differentiate f of x equals this. Now what I'm going to do is teach this two ways. I'm going to use Leibniz's notation, and I'm going to use, well, should we call it a shortcut? I don't know what we'll call it, but maybe a faster method. So the first thing is to spot inner function to the power of 3. So we'll call u our inner function, and y equals, so this becomes u to the power of 3. Right, so let's get du dx equals 4x, and dy du equals 3u squared. Right, so what we'll do is to get f dash x, the derivative, we multiply them together, and we'll do a u substitution at the same time. So let's work out what we have to do. This is going to be 4x multiplied by 3, which is 12x, then u to the 2, now this is u, so let's go brackets, 2x squared take 4 to the 2, and we've got our derivative. Okay, so you can see here Leibniz's notation is pretty quick and involves just repeating this process over and over again. Alright, now here's another method to do it quickly. So if that's my original function, I write down straight away f dash x equals. Now what I actually do at this point here is with my finger I cover up the inner function and simply get the derivative of the outer function. So I write down 3, and then once I've done 3 multiplied by this thing here, I open up my brackets and rewrite the inner function. Drop the power down by 1 and multiply it by the derivative of the inner function. So that's 4x. Multiply it out, 12x, 2x squared, take 4, all squared. And again, you notice that we get the same thing. So that one there, all I do is I cover up the inner function to simply get my quick derivative, and then I've just got to remember to multiply it by the derivative of the inner function. Alright, let's do this one here. So our inner function is this quadratic here, so let's call that u equals x squared, take away 5x plus 1, and y equals u to the 4. du dx is 2x take 5, and dy du is 4u to the 3. Right, that times that with the u substitution. So we're going to go 4 lots of that, so 4 brackets, 2x take 5, u to the 3, now u is this thing here, and we got it. Now you might think, do we expand that? Not really. Do I raise that to the power of 3? No, that is a good enough derivative for us. Right, so a pretty common problem here to see. The function g of x equals f of h of x. They've given us this random table of values here, and they've said here, determine the value of g dash 2. So that means I need to get the derivative of this function here. And you might think, how can you do that without an actual function there? Well, quite easily. I'm going to say that u is my inner function, which is h of x, and y, or g of x, is equal to f of u. Okay, so that's f as the outer function, and u is h of x. Now I'm going to get du dx, which is h dash x, and dy du is f dash u. So the derivative of h of x is h dash x. The derivative of f of u is f dash u. Alright, so now we're ready to apply the chain rule. So the chain rule will be that multiplied by that with the u substitution. So I'm going to say that g dash x equals f dash, so u is h of x, multiplied by h dash x. So there it is. Alright, now that we've got g dash x, we can find g dash 2. F dash h of 2 times h dash 2. Alright, now h of 2. Let's have a look here. Here's h of x. When I pop 2 into it, it returns negative 1. F dash negative 1 times h dash 2. H dash x is there. 2 is there. 6 comes out. F dash negative 1 is f dash. Negative 1 goes in. Negative 5 comes out. And we're done. So this one here requires you to understand how the chain rule is working on functions in general rather than specific functions. Okay, the final one is probably question 1B off a VCAR exam a few years ago. And what we can see is we've got the chain rule. So we've got inner function, outer function. And for a second mark, they want you to put in 1 into the derivative that you obtain. So let's go u equals 2 take away x to the 3, that's our inner. Y equals u to the 3. Du dx equals negative 3x squared, and dy du 3u squared. Right, so what we would do to get our derivative, g dash x, is multiply them together. So that's going to be negative 9x squared, brackets u, which is that, squared. G dash 1 equals negative 9, so 1 goes in there, multiplied by 1, 2 take away 1 is 1, 1 squared is 1. So g dash 1 is negative 9. Okay, so next up, product rule. You should use the product rule when you're asked to differentiate two functions which are multiplied together, hence the name, product rule. So here's an example, linear multiplied by linear, linear multiplied by square root function. Here it is in function notation, but I much prefer Leibniz's notation, where if we've got y equals function u multiplied by function v, then to get dy dx, or to get our derivative, it's simply u dv dx plus v du dx, which rolls off the tongue much nicer than g of x times h dash x plus g dash x times h of x. Alright, so again, just try that versus that, u dv dx plus v du dx versus that, and I think we've got a winner here in terms of how well it rolls off the tongue. Alright, so here is f of x, and it's a quadratic multiplied by a quadratic. So we'll call this first function here u, and second function is v. With the product rule, it doesn't matter which one's u and which one's v, because product has that property where the order of multiplication doesn't matter. So du dx equals 2x take 1, and dv dx equals 2x. Alright, so let's write down our derivative, f dash x equals, so it's u multiplied by dv dx, that multiplied by that. So I kind of look ahead and see if I can do it in a certain way. So I'm going to do the single term first, multiplied by the multiple term second. So it's always plus with the product rule. So it's u dv dx plus that multiplied by that. Alright, and we're pretty much done with that one. I really don't think that there's much else we can do to clean that up. So the way I usually see this, if you lay it out like I've done there, it's u dv dx, so you go across like that, then you go to V, and you go back there. So it forms a nice little cross if you want to use that method. Alright, in class we jumped over example 2 and went straight to example 3, which was the combination of product and chain rules. Okay, so just say we were asked to differentiate this. Let's let f of x equal x plus 5, x take 2 squared. So if I had to differentiate this, I'm going to call the first function, so it's two functions being multiplied together, a linear and a quadratic. So I've got u equals x plus 5 and v equals x take 2 all squared. du dx equals 1. dv dx equals. Now, I could derive this using, or expanding it to a perfect square, and then using the single term derivative rule. But since I've just learnt the chain rule, what I'll do is use that. Alright, now remember what we do, or what I do as a shortcut, is I cover that up with my finger and derive the outer. So that's going to be 2, u would be this thing here, so it's just going to be x take 2, drop the power down by 1, so that's power 1, I'm not going to write that, multiplied by the derivative of the inside. Now the derivative of the inside is 1, so it's simply going to be that. Okay, now we're ready to get f dash x equals u dv dx, so it's going to be 2 x plus 5 x take 2 plus v du dx x take 2 all squared. Alright, so just out of curiosity, I'll just see how the calculator has done this. Alright, so what the calc's done is expand that. I'm going to write it a little bit differently, so I'm going to further engage in this one. Now we don't have to do this unless we're told to do a form-based question, but it might be of interest to us to just see if there's anything we can do. Now, looking at this, I can see that both of them have got x take 2 as a factor, so I'm going to pull out the linear factor, x take 2. Now that is 2x plus 5, so x take 2 multiplied by this gives us this, and x take 2 multiplied by x take 2 will give us x take 2 squared. Alright, now let's rewrite it as and let's collect up the like terms in this second bracket here. And there it is again. So that derivative there, this one here, is exactly the same as this derivative here. So why would I do this when I don't have to? We'll just say part of the problem involves you working out when f dash x is equal to 0. Okay, i.e. you want to find out where the stationary points are. When it's in this form here, you can see here you can just apply the null factor law straight away. So the form will actually help you further engage in some deeper problems that this function might relate to. Okay, but if we're just getting a general derivative, okay, if that is our function there and they just say find f dash x, then this is perfectly sufficient. We don't need to worry about engaging further. Why else might we need to know that this could be written like this? Well, the answers in the back of the book in Cambridge are often the result of further simplification. So I want you to sort of know that it could take this form, or the answer could take this form, or we can see here the calculator will give you this answer here. Now, a good way to check whether your derivative is fine is to use the f of x feature on your calculator. So what you do, pretend that the back of the book has x take 2, 3x plus 8 as the answer to the derivative of this. And you're like, I don't really know how that answer came about. And first of all, this is my derivative and I wonder whether I'm right. So all you do is you type in the back of the book's answer and then you say, is it equal to 2, x plus 5, x take 2 plus x take 2 all squared. And if they are the same derivative, what will happen is you get the smiley face. Ooh, what's happened there? I think let's multiply. Ooh, this is awkward. All right, your rocket scientist of a teacher just realised his mistake. X take 2, 3x plus 8 it should be, not 4. All right, and there's a smiley face. All right, so they are the same derivative. So again, why would we be doing this? That's the back of the book in Cambridge. That's the derivative you got. And just to test whether they are the same derivative, you check it like this and you go, okay, I'm on track. And then you know that it's just going to be the result of some further algebra work that you might have to do. And that's fine. You just chip away at the algebra to find out how you get that to look like that. Right, let's do this one here. So this one here, we need to use the product rule. Now there is a rule that I think will work better with this one, but we'll do the product rule with it. So all I'm going to do is rewrite this as f of x. So let f of x equal x. Now this thing here can be written as x plus 2 to the half. So we can write that as a root function by simply raising it to the half. Now the product rule involves a function multiplied by a function. This is a function divided by a function. So what I'm going to do is just use the negative index rule to do that. Right, so here we've got a function multiplied by a function. U equals x and v equals x plus 2 to the negative a half. Right, derivative of that, 1. Derivative of that. So again, I'm going to use my quick method, which is negative a half gets written down, x plus 2. So the inner gets written down. This goes down by 1, or negative down by negative 2 on 2. So that becomes negative 3 on 2, multiplied by the derivative of the inside. Now the inside of that is 1. So times 1, but don't need to. All right, f dash x equals, so u dv dx. So that's going to be, what's it going to be? Negative x. Now this thing here, what I'm going to do is write that numerator as negative x, and I'm going to grab this negative index and throw it straight to the bottom and rewrite it with a positive index using that negative index rule from a few years ago. Right, so I'm going to write that as 2x plus 2 to the 3 on 2. So I've done that multiplied by that, so that's u dv dx plus v du dx, which is going to be, so I can see here that that's going to be 1 multiplied by that, which is going to just give us x plus 2 to the negative a half. And I'm going to write that straight away as 1 over x plus 2 to the half. Alright, now what else could be done with this? Well, one thing that could happen is this gets multiplied by x plus 2, 2x plus 2 to the half, to the, no, not to the half, to the 1 over 2x plus 2 to the 1. Now, why am I doing that? Well, what that will do is we've got this multiplied together, so we've got common base, we need to add the powers, so that'll become 3 on 2, i.e. what I've just found is a common denominator. So I'm going to continue this up here and say that f dash x equals negative x over 2x plus 2 to the 3 on 2 plus 2x plus 2 over, now these two get multiplied together, so I've got 2x plus 2 to the 3 on 2. Now I can combine my denominators, and what I'm going to do is just play with the numerator. X plus 4 over you can even further engage with that, so that's going to be x plus 4 over 2, and the third, no, so I'm going to write that to the half, so that's the square root, all raised to the power of 3. Right, so there's another way of writing it. So you can see here that we've got heaps of different variations of the derivative. So this one by itself would be quite acceptable. There's nothing wrong with that derivative there. Probably won't match what the calculator does. And so all I've done is further engage with the problem. This is probably a pretty good cleanup of the question. That is to find a common denominator. This one also helpful if you actually have to find like f-2 or something like that. If you have to pop 2 into this, it just becomes something easy to see the square root of something and then power 3 it, as opposed to trying to raise something to the power of 3 on 2, which you sort of might not be able to do. Okay, so there is the product rule. Okay, and the last one we covered, this one will be short and sweet, it's the quotient rule. Alright, so the quotient rule is used when you're asked to differentiate two functions which are being divided. Here it is using function notation. Again, that just doesn't work for me. If it does work for you, that's fantastic. But again, I prefer Leibniz's notation, where if y is equal to u on v, and u and v are two different functions, then this is the rule. So dy dx equals v du dx, take away u dv dx over v squared. So what I say we do is just go plow into it and use it. So we've got one function over another function. So we'll call the top function u. We've got no choice with the quotient rule. The top function always has to be u. Bottom function is v. dv dx equals 3. So we're going to say, and let's go let y equal that. So dy dx equals, so it's v du dx, so it's 2, take away u dv dx over v squared, so that's v, and we're pretty much done. You could expand that, and you could expand that and collect it all up, but really don't think there's any point. Okay, so the last one, top function is the linear, bottom function is the quadratic. Okay, so we've got chain rule here. So again, the way my brain does this, blocks that out, gets the derivative of the outer, 2 x plus 3, power goes down by 1, power 1, multiply by the derivative of the inner, which is 1 in this case, so there's my derivative. Okay, so then we'll say let y equal that. So we can then say dy dx is v du dx, x plus 3 squared. So v du dx, take away u dv dx, 2x, x plus 3, all over v squared, which is x plus 3, all squared, squared. Alrighty, so this one here, power 4. Right, so what else could you do? If that didn't match the back of the book, what I would do is pull out x plus 3 as a factor on the numerator. In fact, let's just do it. You can kill the video now if you don't want to watch anymore. I'm going to go x plus 3 comes out as a common factor. X plus 3, take away 2x. And then that cancels with one of those. And we've got in the numerator x take away 2x. So we've got 3 take x all over x plus 3 to the 3. Can I go on better than that? -1 comes out. No, that's the best I can do. Alright, forget that. So there is probably a more simplified version there. So this is a perfectly functional derivative, it's fine. This is probably just a more aesthetically pleasing derivative. Let's see what the calculator says. Okay, so we'll go diff x over x plus 3 all squared. Yeah, pretty close. Calc doesn't like a negative coefficient on the x, so it'll pull the negative out and give us that one there. So again, my derivative and this derivative are the same, but this is also the same as this derivative. So you can see there that, yep, that's a derivative and it works. That's a derivative and it works. Which one should you do? I think this one is fine early in the paper. This one might help you do things. It might help you with a solve or something like that later on in the paper. Alright, so good luck with those and getting through the worksheet. Let me know if you have any problems.